Okay, so for the conversion lab assignment, this is worth 20 points. And whoops, sorry guys. It's worth 20 points and it is going to be on your lab midterm exam. And so for the due date, look at your syllabus. In a normal semester, it's usually due the fourth week of classes. During summer, it's usually due in a couple of days. So check your syllabus. I want you to complete these conversion problems and be able to do them for the lab exam. I want you to use dimensional analysis to figure out your answers. Make sure you show your work. Don't just write an answer. I need you to work through this. Measurements you should memorize. 1 cubic centimeter or 1 cc is 1 milliliter. 1 inch equals 2.54 centimeters. 1 kilogram is 2.2 pounds, and 100 mils is 1 deciliter. Okay, so what does dimensional analysis mean? Dimensional analysis means you start with 1 unit of measurement, like kilograms, and to get rid of that, to go to the other unit of measurement, you need to put it on the denominator. Okay, I'm going to try to draw this out. Let's see how it goes. So let's say we need to convert 125.5 kilograms to grams using dimensional analysis. So what are we going to do? We're going to start with 125. I want to make sure I'm not drawing all of this. 125 kilograms, right? So 125.5 kilograms. And then we're going to do dimensional analysis. This is something you used in chemistry. So you're going to, why are we doing this right now? We're going to, you use this in chemistry, you use this for drug dosages. So it's important to know dimensional analysis. You're also going to do ratio proportions, but I'm going to save that for your professional programs. So dimensional analysis means kilograms is on the numerator. So you're going to put kilograms on the denominator to get rid of it, right? And then what are we converting it to? We're converting it to grams. So grams goes on the numerator. What's our conversion factor? 1 kilogram, don't make it more complicated than it has to be. 1 kilogram is 1,000 grams, okay? Once you have that, then what do? You're not just gonna calculate it. You need to cancel out your units, all right? So what does this mean? Cancel out like units. So kilograms is on the numerator and kilograms is on the denominator. So you're going to cancel these guys out. What are you left with? You're left with grams. So that's what you want your answer in. So we're done, right? So now you can plug and check. So 125.5 times 1,000 gives us what? 12550. 0, right? Because we're moving the decimal, because we're multiplying it by 1,000, so we're moving the decimal 1, 2, 3, but we're moving back 1, 2, 3. So 1, 2, 3. So 0.5 and moving it back 3 units. So it becomes 125,500 grams. Okay. You're going to convert milligrams to grams, micrograms to milligrams, mils to liters. Convert a patient's height from 5 feet 10 inches. How are you going to handle that? You're going to convert the 5 feet to inches, add your 10 inches, convert it to centimeters. Pounds to kilograms. This is really useful because a lot of drug dosages are in kilograms. So you need to convert pounds to kilograms. You're going to eyeball the person's weight, divide by 2, and that's roughly around the kilograms. Let's see. For number 8 is a little tricky. You've been asked to administer 10 milligrams of drug X per kilogram of body mass to your patient. Your patient weighs 150 pounds. So first you need to convert pounds to kilograms using dimensional analysis in your factor up here, right? So 1 kilogram is 2.2 pounds. Once you have it in kilograms, then you need to figure out drugs. So you know the patient's weight, I think it's 75 kilograms. How many milligrams of drug X do you need? The dosage for that is 10 milligrams of drug X per kilogram of body weight. So that's actually your dimensional analysis or your conversion factor. Then the pharmacy only has gram dosages, so you're going to convert milligrams to grams to figure that out. Okay. The next page. So the next page is dealing with percent solutions. For physiology or for biologists, we usually deal with percent solutions, and it's really fun because you usually don't have to figure out the molecular weight initially. How do we do this? So I can tell you to make me a 0.9% glucose solution, and you just figure out how many grams to weigh, and you add it to 100 mils of water. Okay, so let me do this with you. And this is where you want to pay attention, because this is a little bit complicated. You didn't do this, well, you probably did this in micro. You didn't do this in chemistry, but you did something like it in chemistry. Okay, so 0.9%. How do we convert it from this concentration, which is 0.9%, to this concentration, which is grams per 100 mils? If you remember concentration is always weight over volume, right? Whether you're expressing it as a percent or grams per 100 mils. So here's a trick. Are you guys listening? It's really easy, and that's why we love percent solutions. Let me do this. So playing with colors. It's late. I want to play with colors. How do we do this? Whatever this number is in front of the percentage sign, that's how many grams you weigh out, right? So what did I just say? Whatever number is in front of that percentage sign, that's how many grams you're going to weigh out. And then it's over 100 mils of water. Super easy, right? Okay, let's try it. So, how do we convert a 0.9% glucose solution to grams per 100 mils? It's going to be 0.9 grams of glucose over 100 mils of water. So you're taking it from a percent way of writing concentration to a different way of dealing with it, grams per 100 mils. This you can't use to do different types of calculations. This one you can. Okay, so this is what we're going for. Okay, so in addition to that, I want you to try some on your own. Okay, 0%. So here's a 0% solution. Why am I doing this? For the molecular activity lab, you're going to look at red blood cells in different solutions. And we're going to start talking about osmolarity and tonicity. So I want you guys to do these so that you understand the grams per mils, or how many particles are in each. 0% solution, 0.5% solution, 0.9 is right there. Oops, let's do 0.5, let's do 2%. Okay, so pause the recording now. I want you to work through these. You're converting them from percent to grams per 100 mil. And then once you've done it, go back and start the recording, and I'll go over how to solve this. Okay, so pause it now. Okay, so for 0% solution, a 0% solution, how many grams do you have of particles? If I said go make up a 0% glucose solution, you would weigh out 0 grams of glucose, so no glucose, right? And you would add that to 100 mils of water. So really, what is a 0% solution? Good, it's just water. Whether it's a 0% NaCl solution, 0% glucose solution, it's just water. How do we do a 0.5% solution? So remember, whatever this number is, that's how many grams you're going to weigh out. So 0.5 over 100 mils of water. And then a 2% solution, is it 0.2 or is it 2? Good. 2 grams of glucose over 100 mils of water. Okay, so let's look at each one of these. A 0% solution is 0 grams of particles in 100 mils of water, so just pure water. A 0.5% solution is 0.5 grams in 100 mils of water. A 0.9% solution is 0.9 grams over 100 mils of water. And then a 2% solution is 2 grams over 100 mils of water. So let me ask you a couple of questions. Which one has the least amount of particles? Good, the 0% solution has the least amount of particles, right? And so that has the least amount of particles. What about what has the most amount of particles? The 2% solution has the most amount of particles, right? And you can actually prove this yourself. So 0 grams, 0.5, 0.9, 2. So 2 grams in the same amount of water, you're gonna have more particles. Okay, so when we put particles in water, we call the amount of particles in water gives you a pressure or a pull on water. So the lower the amount of particles, the lower the osmotic pressure of the solution. The higher the amount of particles, the higher the osmotic pressure is. So why am I bringing this up? We're going to talk about osmotic pressure during lab, again with the red blood cells. Okay, so which one has the lowest osmotic pressure? The lowest amount of particles. You can't get any lower than 0, right? So this has the lowest osmotic pressure. Which one has the second lowest? This one, with the 0.5. Which one has the third lowest? The 0.9. Which one has the highest osmotic pressure? The 2%, right? So this is going to have the highest osmotic pressure. The more particles you have in the solution, the greater the osmotic pressure. The greater the osmotic pressure, the greater the pull is on water, right? And so we'll talk more about that as we get into osmolarity and tonicity. Okay, so let's go and look at the other one. So number 10, if you had a 0.9% glucose solution, how many moles per liter do you have? Okay, calculate glucose's molecular weight first. I will give you this on an exam. So glucose's molecular weight is 180 grams per 1 mole. So if you weighed out a mole of glucose, it would be equal to 180 grams. NaCl, what is the molecular weight for NaCl? NaCl is 58 grams per mole, okay? On an exam, I'm just gonna give you glucose or NaCl, and I will tell you the molecular weight. I'm not gonna give you something else, okay? So if you had a 0.9% glucose solution, how many moles per liter would you have? Okay, so you have the molecular weight, you know how to start. So 0.9% glucose, what are we gonna start with? 0.9 grams of glucose. How many mils of water? Good, 100 mils of water. And what are we trying to get to? We're trying to get 2 moles per liter, okay? Because I've done this 100 times, I know, or probably more. I know that we're gonna need 2 brackets, and we're gonna end up with, we want our answer to end up moles per 1 liter, okay? Our molarity is a capital M, and that stands for moles per liter. Okay, so we have 0.9 grams glucose and 100 mils of water. What do you want to deal with first? Let's deal with the grams, okay? So grams is on the numerator. What do we want to put on the denominator to get rid of it? Good, grams. So, and what do we want to get to? We ultimately want to get to moles, so we're going to use our conversion factor that we have, right? So our molecular weight. So our molecular weight's going to go here. Be careful. It's 1 mole is 180 grams, okay? And then what do we do? Before we go any further, you need to cancel out the units because that's going to dictate, let's just do it. That's going to dictate where you go, okay? So glucose, or excuse me, grams is on the numerator. That cancels out. grams is on the denominator, so that cancels out. You're left with moles. Is that what you want for your weight? Yes. So you don't do anything further with the weight. But now we have the volume in mils and we want to get to liters. So we have to figure that out. So how do we convert mils to liters? Good. So mils is on the denominator. What are we trying to get to? Okay, so we need to put mils on the numerator because we're trying to cancel the mils, and liters is on the denominator. What's our conversion factor? Don't do 10 to the negative 3. 1 mil is 10 to the negative 3 liters, and you don't need to do in scientific notation because that just messes everything up. I know you spend all this time learning that in chemistry, and then I tell you not to use it. But make it as simple as you can, okay? So 1,000 mils is 1 liter. All right, so then what do? You're gonna cancel out your units, right? So mils is on the denominator and mils is on the numerator, so you cancel those out. So what are you left with? You're left with liters. Is that what we want? Yes, we don't need to do anything further. So you can calculate it. So it would be 0.9 divided by 100, hit the equal sign, divided by 180, hit the equal sign, times 1,000, right? Or because you have 1,000 here and 100 here, you can cancel some zeros. Let's do this color and see how it works. How many zeros do we have on the numerator and how many do we have on the denominator? We have 2 zeros on the denominator, so we can cross those out, and we can cross out 2 on the numerator. So I'll use this with 10. So 0.9 times 10 gives us 9 divided by 180. So do 9 divided by 180. For your lab exams, you guys, for your midterm and final, you should have a basic calculator that you can use. And obviously you can't use the internet or anything else or this homework assignment. So make sure you know how to do these and you can practice these. So let's figure out the answer first. So 0.9 times 10, which is 9 divided by 180, gives you 0.5. Is it 0.5 or 0.05? Let me see. 9 divided by 180 is 5, so I think it's 0.05. Oops. Yeah, 0.05. I just wanted to double check because it's late and my brain's not working. Wrong pen again. Okay, so 0.05. Oops. Sorry, guys. Stop. Oh, seriously? Okay. So 0.05. Okay, are you gonna draw or what? Okay, so 0.9% glucose gives us 0.05 moles per liter. So that's how you would solve that. What I recommend, or what I was going to say, is once you finish going through all these, do calculations for the ones at the top. So what is a 0.5% solution going to give you as far as moles and osmoles? What is a 2% solution going to give you? And you can make up solutions and do these calculations. You can start with any percentage. It doesn't matter. You can do 0.5, 0.9, 0.1, 1%, 2%, 5%, 10%, whatever, until you are confident that you know how to do this for the exam. Okay, so this next one is how many osmoles per liter do you have? You can start from this. So you can start from 0.9 over 100 mils and calculate this all the way through moles per liter, which I recommend. But for time's sake, I'm going to start with 0.05. For my students, when I'm grading this, I prefer you not to start with this because if you got this number wrong, you're going to get all the other calculations wrong. So start with 0.9 over 100 mils and calculate it through. It's good practice too. Okay, so how many osmoles do you have? So let me explain osmoles. Osmoles, so moles is moles per liter. Osmoles takes into account how many ions it disassociates into. Okay, so if we have glucose, how many ions does glucose disassociate into? It doesn't disassociate into any ions. It's not a salt. Okay, so 1 mole of glucose gives you 1 osmole of glucose. Okay, or we can write it to the left of this, 1 mole glucose, right? Add it with water, is going to give you 1 osmole of glucose. So your conversion factor is going to be 1 to 1, right? So you have moles on the top. What goes on the bottom? You can pause it now and see if you can solve it, okay? And then come back and check the answer. So pause now. Okay, so this is moles, right? And then you want to convert it to osmoles. What's your conversion factor? 1 mole of glucose gives you 1 osmole. And then you cancel out your units. And so it's going to be 0.05 osmoles per liter. This should make sense. So a 0.9% solution is going to give you 0.05 moles per liter or 0.05 osmoles per liter if we're talking about glucose, because glucose doesn't dissociate in water. Okay, let's go to sodium chloride. So you can do number 12 now on your own. Number 13 is osmoles per liter. Let's see. Okay. I think for number 12, let me see, number 12, you should have 0.155 moles per liter, right? And so if we have 0.155 moles per liter, and we're converting it to osmoles, NaCl, how many osmoles does NaCl, or how many ions does NaCl break up into? Right, let's try that. So 1 mole of NaCl, when you add it into water, what does it do? It ionizes, right? So you have 1 mole, and listen to this carefully, or listen to it twice or 3 times. You have 1 mole of Na plus, right? And 1 mole of Cl minus. So how many particles do you have in solution? So you had 1 mole of NaCl, you stuck it into water, so you had table salt, stuck it into water. How many particles do you have? You have twice as many particles because it separates. So you have 2 osmoles. It's really important to understand that when you're dealing with salts like NaCl or potassium chloride or calcium chloride, that whatever moles you have, when you put it into the plasma or when you put it into water, it's going to separate into its ions. So you're going to have twice the amount of particles or 3 times the amount of particles. And so that's going to dictate the way that water moves. Okay, so for NaCl, it's a 1 mole to 2 osmole ratio, right? This you have to memorize. So moles goes on the bottom and osmoles goes on the top. So 1 mole gives you 2 osmoles, right? Then what do? Cancel out your units. 0.155 times 2 gives us what? 0.3 or 308, 300, depending on how specific you are. Okay. Then you need to figure out milli. So 1 osmole gives you how many milliosmoles? 1 osmole gives you 1,000 milliosmoles. Okay, so you can figure that out. It's like a liter and 1,000 liters. Okay, so work on this. Make sure you understand this for the lab exam. And let me know if you have any questions.